Okay, everyone, I just wanted to take a couple minutes to go through your Hubbard Brook example to make sure everyone understood it, because this, like many of the things we're going to focus on in class, is really centered on making, but more importantly, understanding the information that we can get from graphics. And I can't express enough how much of a focus that is. We really focused on it in our discussions, and we're going to focus on it a lot in everything that we do. Every single unit, I'm going to pull up the graphs from the unit to make sure that we really understand what's coming out of there, and it really is going to be a center on your test questions as well. You can get whole questions correct just because you understood the graphs, and that's something that you'll see in your future career, on your graduate school exams. So this is really a key feature that we focus on in this. It's an outcome for this class. So from your Hubbard Brook, one of the first questions is looking at, let's see if we get my pointer here. Can get a laser pointer? Can. Let's do that. Okay. Is to look at graphing stream flow, which are my two blue lines here. And this is all for the early years, right? So before the experiment takes place for watersheds 2 and 3. And then to, on top of that, graph the precipitation for those two streams. So one thing that we see right away is that the precipitation for these two streams is identical, pretty much, right? And that's not surprising. Remember, the image for these two valleys shows that they're right next to each other. So you wouldn't expect that the weather, right, the local weather for these areas would be significantly different. Remember, when we're doing line graphs, so we're tracking a single thing, precipitation, over something, in this case time, that you're going to do a line graph. And when we do our line graphs, that you really want to do a scatter plot and then connect those with a line. In this case, I've chosen the curvy line because it's more aesthetically pleasing, but you could have chosen the sharper line, it doesn't matter. Okay, so here we have the precipitation. Those are the same. Now here's our two watersheds, watershed 2 and watershed 3. And these are fundamentally the same. Now, we don't have enough data to put error bars in here, but there's not a huge difference here between the two watersheds of stream flows, right? This is what's coming out of that. Let's get a pen here. V8, there we go. V-shaped weir. It's my water, which is also red. Now, the key here is while the water flow is the same, okay, there is a significant difference between total precipitation and total stream flow, right? It's different. And so the first question you need to ask yourself is, what is driving this difference? Okay, and so certainly our main answer here should be, am I just getting, nope, it's just not drying. Vegetation, right? So this is being soaked up by vegetation, right? Or this is our main hypothesis, at least. Okay, so the trees and the plants, the shrubbery, okay, whatever the case is likely, okay, soaking up a lot of this precipitation and performing evapotranspiration, okay, cycling it back up, creating the water cycle here. Okay, and so here, okay, we see, man, this thing does not want to draw for me. The same two streams, this is the same line graph, okay, just this doesn't have the precipitation business in it, but this is carrying on past 1965 or 1966. This is a longer data set. And now we can see, okay, that one stream bed has significantly lower or less stream flow and one has more water. Okay, so our blue bar, or our watershed 2, okay, you would imagine would have a much faster or stronger or more total water coming out of that V-shaped weir than our red bar here, our watershed 3. Okay, so remember then, in this case, this watershed 2 is the sort of the deserted wasteland of the two watersheds. Okay, if we go back to our image, it's the one all the way on the left that looks dead, right? This is where we've removed everything, and you can really see that granite under the soil, right? It's very dead. We've removed the vegetation here. Whee! So here we start to get an inkling at what effect vegetation really has the overall stream flow. Okay, and it's several hundred millimeters per area per year of total annual stream flow. Okay, and in fact, what we found for our case study, okay, so now I flipped colors, sorry about that, guys. See, but this is still the deforested, okay, so we have, in this case, we had more, more total flow on the previous graphic, and this had less flow. Okay, so this one wasn't cut. Okay, when we cut all that vegetation down, not only did we increase the flow of water, but with that water came everything else, right? So not only was the water going with, but everything that's in the water was going with. And in fact, it was pulling out stuff that was in the soil already, okay? So this is what we call erosion or runoff, okay? And these are big deals, right? These minerals that we talked about, things like calcium, and iron that would already be in the soil, the animals are traversing a really long distance to go to. But on top of that, right, things like nitrate, okay, or phosphorus that normally, okay, would be nutrient limiters. And remember, in this case, we're on the top of or part of a mountain. Okay, so nitrate is a bigger limiter than phosphorus is for the most part. So all of these things are getting pulled off of that mountain. So this makes this mountain have a lot less nutrients, which is problematic for everything that is actually living up there. That's its own issue. So less on the mountain. That's a sad face. Okay, because it's all running off. Okay. What's even bigger is that runoff has to go somewhere. Okay, well, bigger depending on your perspective. Everything's dead there right now, right? So all of that water that's coming out of the weir, okay, is running into that valley, right? And people live, animals live in that, in that valley. And so all of this stuff is now in that runoff at significantly higher concentrations because it's been in the rainwater and it's not getting absorbed by any plants, and it's been pulled from the soil. So it's been like super concentrated, super duper concentrated. Okay. So all of the water at the bottom of the river, very concentrated, up to the point where the EPA ultimately called it unsafe for drinking. Okay, so this sort of harkens to our town hall debate. Okay. Except the EPA made a decision. You guys can't drink this anymore. This is a super problem. Okay. So this actually was a huge issue. So we really got to understand what is the role that vegetation plays. Okay, so here's our graph from 2 slides ago, extended even further. Okay, here, please draw for me. Here's the original graph. Okay, where we saw they were the same. Okay, here was the first expansion of the graph, where we could see the cut. Our blue is the cut. Okay, so we had more runoff. And this was the control. So we had less runoff. Okay, but after the 1970s, we didn't continue to cut it, right? This was sort of a one and done business to see what would happen. And so after, okay, this happened, we see that over time, okay, that our two watersheds come together again. And so by here, we once again see we have the same output. Okay, and so this is off of your Hubbard Brook Go for the Flow again. This is a graph that you would have made. And so what is this telling us? Okay, what is our hypothesis about this one? Well, this is telling us that no matter the precipitation again, that if our two watersheds have the same weir output, okay, that because we're not continuing to cut, that we're seeing some veggie regrowth. Pardon my shorthand, but it's hard to write with a mouse. Okay, and that veggie regrowth is once again, in both cases, right, creating the same evapotranspiration. I really chose to write that word. Okay, where the water is getting absorbed. Oops, I did so good until the end. It's getting absorbed up the roots, getting carried up the trees or the shrubberies, okay, and then completing the water cycle. So we really do see, in this case, a very powerful effect of vegetation on both the water cycle and many of those nutrient cycles that we've been studying. Okay. So make sure this process makes sense. So the interconnectedness of vegetation on our nutrient cycles, and of course that the bearing of this information from these graphics makes sense.